Going back to our modes of vibration, we don't only see modes of vibration by setting initial conditions in systems. Especially in the real world, it's very rare that we actually take physical systems and move them to exact locations and let them go. It just doesn't happen. Where we see an analog to that, though, especially with vibrations, is if you have an external force at the same frequency. If you want a concrete example where this comes up, if you've ever sat, especially in an older car with looser pieces, when the engine's vibrating, then various parts of the car will start to vibrate in response to the engine vibrations, depending on the frequency of the engine. So as you hit different speeds and hit different RPMs in the engine, various bits of the car will vibrate more or less. What you're seeing there is that the piece of equipment other than the engine has a mode of vibration, and then when it's hit by the frequency of vibration from the car, it responds most strongly when those frequencies match. Mathematically, we call that resonance. When we had a single mass system, when we applied a force with the same frequency, we ended up having that growth in amplitude. So the system responded by having larger and larger amplitude oscillations. When we study this two-mass system with these springs and masses of 1 kilogram, we get these eigenvalues, which dictate the solution form. We're going to have cos of 2.8t or sine of 2.8t's, and we're going to have sine of 1.07t's and cos of 1.07t's. What happens then if we just, to either mass, start applying a force that has a frequency? It can be a very small force, but some F external that looks like cos of 2.8t. Well, what we've said is that this system will naturally vibrate at cos 2.8t. So what we're going to get when we push on this thing and pull on it at exactly the same frequency, and this system is going to give or display some resonant behavior, but it'll be more interesting than it was before. We'll get resonance, but the solutions that are a multiple of the eigenvectors here for the lambda equals 2.8i plus or minus case. And in particular, if we look at these four variables as position and velocity of x1, x1, x2, and x2, what would this look like? Well, here we see that x1 is going to have a negative position and x2 is going to have a positive position, so this is going to cause the vibrations where these are out of sync from each other. They're moving in opposite directions. So when we oscillate or force this system at a frequency that matches this mode, we're going to see negative displacement and positive, so oscillating out of sync or in opposite directions. If we wanted to, we could also force with a different frequency. That would produce a different kind of behavior. It would produce the behavior where both masses are going in the same direction. These have the same sign, but the second one's a bit bigger. So the second mass will go out further and then come back, and the first mass will be going out and then back, and they'd be going in the same direction at the same time because these values here have the same sign. Again, so much clearer with the demonstration, which we're about to get to. However, we do want to explore one last system here before we get to the animations, just to see the range of behaviors we can see in even more complicated structures, like a 3-story building. This 3-story structure can be modeled as a sequence of springs and masses. The idea is if the displacement of each floor, left to right, is given by an x value, x1 through 3, then what we can do is imagine a spring and a mass and an equilibrium point for x1 for that mass, spring and a mass, spring and a mass, and then the equilibrium points for the other two coordinates, x2 and x3. We get the same kind of behavior as this. These columns are like springs because if you distort them, they want to push back. Springs are like that. When you distort them, they want to push back, and you can produce oscillations that way. Here we'll produce oscillations horizontally. The math is identical. It's identical between these two cases. And what that means is when we look at how a building will demonstrate or elicit modes of vibration, it'll be the same as when we elicited modes of vibration in a spring mass system.